Part of the calculation of multidimensional heat conduction in buildings is also to note the very important heat loss that we have from buildings in the vicinity of foundations. So here this lecture will be about describing a methodology, how to calculate that, which is a methodology from the Danish standard 418. One annex to that standard, Annex D, describes this methodology. So we look to the foundation under a house. We have, of course, the room, the soil below it, and then we have the outdoor air as the components. But I'll draw it a little bit also more over here on the whiteboard. So here we see a zoom of that foundation with the wall, with the slab on ground floor here, the foundation itself, and then the soil outside here. The methodology to calculate lengths from methodology to calculate thermal bridges otherwise also. So for thermal bridges in standard terminology, we use the letter psi, and we're going to find the psi value for the foundation, so psi-f in this case here. The methodology normally says that you have to use a multidimensional heat flow calculation program to analyze the total heat flow through the multidimensional construction that you have. And then you subtract from that normal one-dimensional heat flows, which you can see are involved in the process, and the difference between the accurate way everything is calculated and the simple way you have only one-dimensional, that becomes the thermal bridge and can be put down in numbers like the psi value, for instance. So in this geometry, we should calculate the whole domain. Then we should calculate the one-dimensional, or we should subtract from that the one-dimensional heat flow through the wall. So we're interested altogether in the heat flows through the wall, and likewise also in the heat flows going into the structure through the floor. Those two red lines together, the heat fluxes over that, in total gives the total heat flow through the whole system, and then after that we subtract, as I said, the 1D from wall and floor. That will give us the psi value as shown here. But we should adopt some climates, and we should do it in the way that the Danish standard prescribes. And the rest of my talk will go here on the PowerPoint slide here. So the boundary conditions for indoor air, well, we take the normal 20 degrees and normal surface resistances for the different surfaces that are involved, as we saw on the wall and on the floor. Outside air, that's important. Because these calculations cannot be made in a steady-state manner. The heat flow into the soil is so slow that we have to consider the seasonal variation and the long time it takes before everything comes into equilibrium down in the soil. So we should consider the outdoor temperature by this sinusoidal change that describes seasons, winter and summer, of course, and the periods in between. So we insert the months in this equation. If we can go over here for the last time here on the outside, well, that means then that the outdoor temperature is described by this seasonal sine curve. So that gives us the outdoor condition. Indoor was the temperature here for the wall as well as for the floor. We need one more point, which I'll come back to later in the presentation, but we need a point to describe the kind of cold temperature that we have down in the soil. I'll come back to that on the slide over here. So as we continue, that was our sine function for the outdoor temperature. We calculate things monthly, although we might have to calculate several years as it happens. But we take the whole year, month by month like this, and we're interested in the results in the end for the 9 coldest months. So altogether from September going to May will be the calculation period that we should end up finding. On average, for those 9 months, we have an outdoor temperature of 5.54. That's another number we need to know to represent also the outdoor climate. Here's the geometry again, because the standard prescribes a little bit further that we must calculate 20 meters down into the soil and 20 meters away from the building. And below the floor, we should take 4 meters into the building from the interior surface of the foundation. And the wall, we should go 1.5 meters up. So that's specified as a calculation domain. Here's the reference point. So in the 4 meters depth into the building or from the surface or from the foundation, then just below the construction layers that we have in the floor, that's where we have our reference point for what is the temperature down in the soil. Okay, so we should use advanced numerical programs to calculate this. They have a mesh for making the numerical calculations, And there's some text in the standard that prescribes how you should make a fine mesh, but not too fine, and it takes too long for you to wait. So you must refine the mesh such that further refinement does not improve the results significantly. And there's some formal text how that can be phrased. But normally some elements for numerical measures which are like in the centimeter ranges, a couple of centimeters perhaps. Then the calculation period, I've indicated already, you might need to calculate possibly several years because you need to calculate these variations seasonally, and you have to calculate year after year such that the last year looks more or less like the previous year. The results must not be more than 1% different from what you obtain one year to the next. Okay, if we make an example of a geometry more or less like I've drawn on the whiteboard, well, then in the last year of calculation, well, then the advanced program I'm using comes up with a heat loss in total for those two red lines. Perhaps the camera should go over here again still. But the summation of heat loss through those two red lines in each of the months of the last year comes to as a power per meter length of the building with these values here monthly. Also the reference point, I was interested to know what's the temperature, and here we see also the program's calculation of the monthly average temperature in that reference point. And we were interested only in those 9 months altogether, which are now in the frames here. And there we can see an average specific heat loss there, 16.35 watts per meter, and we have in a reference point an average temperature for those months of 13.12 degrees centigrade. So, okay, now with those outdoor temperatures, the 5.5, and here in the reference point, what was it, 13 degrees centigrade, well, then we can calculate normally one-dimensionally, since we know U values of the wall, we know U values of the floor, we can calculate what would be the normal heat loss through those two structure elements. And that will then, when we insert those temperature differences, 20 minus 5.54, then we get this heat loss through the wall in the 1.5 meters height. And for the floor, the 4 meters floor, and with that temperature, as I've now mentioned a couple of times, then we get this heat loss through the floor. That is if we had calculated things only one-dimensionally, but our program had calculated also more correctly, so it got 16.35, and we subtract the one-dimensional heat losses from that, well, then we get the difference, and we calculate that difference per degree difference between indoor and outdoor temperature. Then we get a specific heat loss as a linear transmission heat transport coefficient for the foundation CF of 0.25 watts per meter Kelvin. So that's a long methodology. We have to adopt an advanced tool and subtract from that some simple things to get this result. That was the methodology. I hope you appreciated this lecture here. Thank you for now.